Hello everyone, welcome back. Today we are going to look at the method of characteristic. This is a very elegant way to solve first order partial differential equation. Let's start with the general form of the quasilinear first order PDE. That is ax y ux plus bx y uy equal to c x y with the initial condition ux0 to be equal to f of x. We want to find a curve along which this PDE just behaves like a simple ordinary differential equation. To do so, we introduce a parameter along the curve, and this parameter has the coordinates. So we let x of s and then y of s depend on the parameter s. So basically we can visualize the whole thing as this. So we have our function u, our known function u, and then u depends on x and y, and then x intends to depend on y, on s, and then y also depends on s. So this is what you have. And so if you want to differentiate u with respect to s, then what do we have? We'll have, if you differentiate along this path, you're going to have ux, and then you have the x over the s, and then the same thing here, we'll have uy, and we have the y over the s. So by applying the chain rule, we'll have the u over the s of u of x of s and then y of s to be equal to, so we are going along this path, and we'll have ux multiplying the x over the s plus uy multiplying the y over the s. Alright, so if you apply the chain rule, this is what we have. And so we have this differential equation and we have this equation. So we compare this one to the main one, the general form of the quasilinear PDE. And so if you do the comparison, you can see that here ux is, the coefficient is dx over ds, and so if you compare, that means that dx over ds is equal to axy. So we'll do that. So we'll have, for the first one, we'll have dx over ds is equal to a of xy, which implies that if I make ds the subject, I have ds to be equal to dx over a. Alright, then we do the same thing for y uy. So in that case, you have the coefficient dy over ds to be equal to b of xy, and that implies that if I make ds the subject, I have the s to be equal to dy over b. Then clearly we do the last one for the u. So we have the u, so the u over ds is equal to c of x, y, and u. And then you agree with me that if I make ds the subject, so making ds the subject, I have the u over c. Alright, now we have the s here, the s here, the s here, so we can say that they are all the same. And so when we equate, what are we going to have? We'll have the x over a to be equal to the y over b to be equal to the u over c. So this gives us the characteristic equation. That is, this is the characteristic equation we are talking about. So this is okay. But when we are given the general rule, we attach an initial condition to it. And then the condition that was given to us was for the PDE. It was not for the ODE that we have generated. So in that case, what we have to do is that we have to generate an initial condition for the ODEs that we generated. So in that case, we'll say that if x depends on, if we substitute 0 for s, then we can say that x of 0, we can say x of 0 to be equal to s, and then y of 0 to be equal to 0, which implies that if that be the case, we have u of 0 to be equal to f of s. So we can say that if we pull this p from the PDE, we get x to depend on 0, and then that will give us s. Then we have y of 0 to be equal to 0, and then we have u of that will imply that u of 0 is equal to f of s. Alright, so that is that for this one. We take an example. Alright, so let's take this example we have here. Okay, so from the example we can generate equations. So by method of characteristics, we can say that the coefficient of t or ut is 1. So we have the t over 1 to be equal to the coefficient. So we have the x over e negative t, and that should be equal to. Now if you take the other one, we have the u over negative u. So in simple terms, if the equation is given to you, the ordinary differential equation of the partial differential equation is what we use on top. So as you can see, ut, so we use the ordinary differential equation, that is the t over the coefficient of that. Here it is ux, so we will use the x over the coefficient of that, and then here it is u over the coefficient of that. And so this is what we have. Now from this one we can generate two differential equations from here. We can generate two differential equations from what we have here. So we can have the t over 1 to be equal to the x over e raised to power negative t. Now by solving, we can have this one to be the x over the t to be equal to e raised to power negative t, and then we'll give it the initial condition. So from our initial condition, we said that for the derivative, when we have that, we have x of 0 to be equal to s. So let's label this one equation 1. Then we'll do the same thing for the other one, and we can also see that this one we equate it to that, and we'll have the t over 1 to be equal to the u over negative u, and that will give us the u over the t to be equal to negative u. And so we have the initial condition to be u of 0 to be equal to f of s. So let's label this one equation 2. So we now have our equation 1 and then our equation 2. So from equation 1 we can say that if we have the x over the t equal to e negative t, we can use separation, right, to solve these things. So we can have this one to be implying that the s is equal to e negative t dt. How do we go about that? We can integrate here and integrate there. Now if we integrate, what are we going to have? We're going to have, okay, from equation 1, we can say that the x over the t being equal to this. So we can use method of separation to solve this particular ODE, which will imply that we have the x to be equal to e negative t dt, right? Now we integrate this side, we integrate that side. Then what do we have now? We'll have x to be equal to, so when we integrate what we have, then we have negative e negative t plus a constant. So wherever you add a constant, it's okay. So we'll have that. Now we apply the initial condition to find the constant term that we have there. So to apply the initial condition, so now x of 0 is equal to s. So wherever we see x of 0, we put x of 0 there in order to find our c, that's our constant. And so in that case, we will have x of 0 to be equal to e negative of 0 plus c, and that will be x of 0 will be equal to what? Will be equal to 1, right? Or negative 1, sorry. So x of 0 will be equal to negative 1. But we know what s of 0 is. That is what? S. So we have negative 1 plus c. Then we have s to be equal to negative 1 plus c. Now if you make c the subject, because that is what we are looking for, so we make c the subject, we have c to be equal to s plus 1, and that is what we have. So we have been able to find our variable c. So we substitute c back into the equation we had, and then we have x to be equal to negative e negative t plus s plus 1. And so this is what we have, right? Okay, so now as we have been able to find our value, we can make s the subject, and if we make s the subject from here to, we'll have s to be equal to x plus e raised to the power. So this is what we have. Now we solve the second equation, equation 2, and so when we solve the second equation, we're going to have du over u to be equal to negative dt. That is when we separate the variables. Now if I integrate both sides, what do I have now? I have ln u to be equal to negative t plus the constant. Let's say let's use k in our case here. Now how do we get our u? We take the antiderivative, anti-log of both sides, and then we have u to be equal to e negative t plus k, right? So in that case, we can split that. We know that this one is the same as writing e raised to the power negative t times e raised to the power k. You all agree with that? And so if that be the case, we can label all this one as a constant, one constant. So let's say k1. We have u to be equal to k1 e raised to the power negative t. Now we apply the initial condition to be able to find k1. So to apply the initial condition, when we apply the initial condition, u of 0 to be equal to f of s, you have u of 0 to be equal to k1. Wherever we see t, we put 0 there, so we have negative 0, and that will give us u of 0 to be equal to k1. But we know u of 0, that is f of s, so we have k1 to be equal to f of s. But that, so in that case, we go and substitute that back into the equation, and we have u to be equal to f of s multiplying e raised to the power negative t. But we know s already, so since we know s, we substitute s back into the equation, and then we have u to be equal to f of our s that we had x plus e negative t minus 1. So x plus e negative t minus 1 times e negative t. And so that is the general form. So this will be the solution of the PDE given to us earlier on.